All right. All right, so today's lesson is about more special roots. So we talked about special roots in our last lesson. This is an extension of that. We're continuing on to a different type of special root. That special root, spoiler alert, is going to be imaginary roots. So remember, we've talked about how if you have roots, a lot of times, yes, they're x-intercepts, but they're also the values that make the equation true when you set it equal to 0. So sometimes that's an imaginary answer. Just like in our quadratic unit, we had imaginary roots. Well, we're going to have imaginary roots with cubic functions, quartic functions, and so on. All right, so for your warm-up, it was an attempt to find those roots. First of all, you should be able to find some of them based on what we know, and then we're going to go from there. Now, obviously, you would be trying to figure this out on your own. This is the explanation of how the warm-up would be completed. Okay? So if you're looking at this function, well, you're given the function and the graph, right? And you're asked, what's the degree? Well, you can find that out from a couple different ways. First of all, it's highest powers to the third. So we know the degree is 3, right? And we can also look at the graph and see it's a cubic function. It has 2 turning points. Therefore, it is, we know it's, first of all, we know it's odd because it starts at the bottom and to the top. 2 turning points means it's going to have be a third degree function. It should have 3 roots, right? So we're trying to find those roots, right? Now, looking at the graph, we notice we have an x-intercept of -2, right? So the first root we found was -2. We're still looking for 2 more. Now, in yesterday's lesson, we talked about, oh, well, maybe it's a double root, maybe it's a triple root, right? But then we learned that a single root just crosses, a double root bounces, and a triple root changes concavity. So if we look at this root, this -2, and we look at the behavior, we can see that this root just crosses the axis, right? It doesn't change its concavity, right? It doesn't go from curved up to curved down. It doesn't bounce, right? So that means it's a single root, right? We're not dealing with a double or a triple root here. So if we know that this is a single root, because it just crosses, that kind of leaves us with 2 question marks here, right? How do we find those other roots? Well, the other thing we talked about yesterday, during our warm-up yesterday, was, well, if we know a root and we have to try to begin to find the other ones, we can start to factor, right? And this is the key piece here today, right? If we know a root, we can start to factor and continue that process, right? See if it gets us anywhere, right? So think about what we know. Well, we know the function equals x to the third minus 2x plus 4. And then we know that a factor, a root, is -2. So a factor is x plus 2. So this must equal x plus 2 times something, right? To find that something, well, we can divide, right? Just like if you divided 6 by 2, you'd get 3. If I divide this by this, I'll get whatever the rest of this is, and then I can see if I can continue to factor it, right? So I go ahead and do that with synthetic division. Remember, the root was -2, and then the pieces inside are 1, and then we have 0, -2, and 4. And because we know that this is a root, we can see it on the graph, we should expect a 0 here, right? We'll confirm that, but we should expect a 0. This should divide evenly. It should give us a jump start on our factoring. So I bring down the 1, multiply, get -2, add, get -2, multiply, get 4, add, get +2, multiply, get -4, and indeed those add to give me 0. Well, what did I determine? I determined that this divided by this is this, right? So I'm going to put that as the rest of my piece here, right? So it turns out this equals x plus 2 times this part right here. So that is x squared minus 2x plus 2. Okay, now we want to try to continue to factor that. Well, we have a quadratic, so we would say, hey, maybe I can magic x that, right? So I'd go and I'd try to magic x it. And I'd say, okay, 2 on the top minus 2 on the bottom. Maybe I can break this down into further factors. But then when I go to do it, I think, well, the only things that multiply to give me 2 are 2 and 1. 2 plus 1 is not negative 2. Even if I made them both negative, negative 1 and negative 2 are not going to add to give me negative 2. So this turns out to not work, right? This is not factorable any further. All right, so we have this situation where we can't factor any further, right? And we're trying to find our roots. We're trying to find when our y value is 0. Well, let's just write what we're trying to do and go from there, right? So we're trying to find when f of x is 0, and this is as far as we've been able to factor it. X plus 2 times x squared minus 2x plus 2, right? We decided we can't factor that any further. Well, if we can't factor it any further, anytime we're equal to 0 and we can't factor any further, we do have a step that we're supposed to go to, which is the zero product property. So at this point, I would break it apart, even though it's not all binomials. I still would say, well, this is as far as I can go, so I'm going to solve each one. That means x plus 2 equals 0. X equals negative 2. That's the root we already knew. So that's the easy part. And then I have x squared minus 2x plus 2 equals 0. And I have to solve for that x in that one. Now, I can't magic x this. I can't do any other things. But we do have a way to solve when we have a quadratic that equals 0. And yes, that is the quadratic formula. So we're going to use that quadratic formula. We'll do that over here to figure out what the x is that makes that true. So we'll say, okay, x equals, remember it's negative b plus or minus the square root of b squared minus 4ac all over 2a. So I plug in my a, b, and c, and I see what I get. X equals negative 2, so that's 2, plus or minus the square root of negative 2 squared minus 4 times 1 times positive 2, all over 2 times 1. So this turns into x equals 2 plus or minus the square root of, we'll figure out what that is, over 2. Okay, so what is that? Well, we put this into our calculator, negative 2 squared minus 4 times 1 times 2, and we get negative 4. So this turns into 2 plus or minus 2i over 2, right? If you have negative 4, well, that's square root of negative 1 times the square root of 4. So that's plus or minus 2 times I. So that's 2 plus or minus 2i. Now, this is 2 plus 2 divided by 2, so we can actually do that division, and we end up with 1 plus or minus I. So it turns out our other two roots are indeed imaginary. So coming back to what we were trying to figure out here, if we were trying to figure out what's the x value that makes this true, well, it is x equals 1 plus or minus I. And those are our other two roots, right? So let's take a step back here. What do we have? We have one real root, which is negative 2, and we have two imaginary roots, which in this case is 1 plus I and 1 minus I, right? Those are our three roots. Now, if we look at our graph, that makes sense. We only had one x-intercept. It was a single root, so it wasn't a double or a triple. So our other two roots must have been imaginary roots, right? to get us to the 3 roots that we need for a cubic function, right? So that's where we're going today. We are trying to find those missing roots, even if it requires the quadratic formula, even if it requires solving for x when we can't factor any further than a quadratic, okay? There's also going to be one other scenario where we get imaginary roots when we isolate the square, but that's our challenge for today, okay? So let's take a look at, let's define imaginary roots again, and then we'll look at some examples. So imaginary roots, again, are solutions to a polynomial that include I and are not x-intercepts. Okay? They include I, they're not x-intercepts. Okay. Now, a couple things to note here. They always come in pairs, meaning even amounts. You will never have one imaginary root. And that should make sense because anytime we get imaginary roots, it's because we were square rooting a negative. Anytime you square root, you plus or minus. So you're always going to get the plus or minus I situation if you're square rooting a negative. Okay? Now your possible roots, so that's a good thing to know. Like if you know what your possible roots are for an equation, then you know, and you can see a couple of them, or you can see one of them, you know how many are left that you can predict will be imaginary. So possible roots is a good thing to think about before you get started. Your possible roots are one more than your number of turning points, right? So turning points, again, are those times where the graph's going up and it starts to go down, or it's going down and it starts to go up. So if you count them, then you'll know your possible roots. It's one more than that, right? And we'll look at some examples, okay? So let's take a look at this first example. Now, we look at this and we know it's cubic, right? Or we think it might be cubic because it kind of looks like a cubic function. So we would say our possible degree here is 3. Now, we could also look at the turning points, right? If I see I have this goes up, and then it starts to go down, and then it goes down, it starts to go up, it has 2 turning points. So its possible number of roots is 3, right? Now, if I take a look at this, I see there is one real root here, and it's a single root. So just like our example in our warm-up, right? That's a single root, so I have one real root, which means I must have 2 imaginary roots. And that's the math you always want to do before you start doing this stuff, because then you know what to expect. You know what you should be solving for. You know how far you're going to be able to factor this before you have to just solve a quadratic with what you got, right? So we're going to do this a couple times, right? And just make sure that we are doing the math on how many imaginary roots we should expect, right? Here's an example. Well, we're looking at this. Maybe we remember that this looks like a quadratic function, so we say it's a possible degree of 4. But we could also think about the possible degree, by the way, is the possible roots as well. So our possible degree is 4. Maybe we remember that it's a quadratic function, but what if we get to like 6 or 7? We still want to be able to figure this out. So we look at these turning points. Well, there's one here, there's one here, and there's one here. So there's 3 turning points. And remember, it's always One more than that will be our possible roots, right? Now, if we think about our possible roots, well, here we go. That's our x-intercepts will get us started. That'll tell us our real roots, right? So I see I have a root here, here, and here, right? Now, we got to look at what happens. This is our last lesson. Here, it bounces. So I have a double root. Here and here, it just crosses. So that's two single roots. So think about that. I have two real roots here, and then two real roots here. So that's 4 real roots, right? So the number and type of roots is 4 real, and we've used up all our possibilities, right? There's only possible was to have 4. There's 4 real, so there must be 0 imaginary. All right, one more like that. Okay, here we had a crazy one, right? So this will be harder to be like, well, it kind of looks like it to the 3rd or to the 4th or to the 5th, right? So we're going to look at our turning points, right? Well, here's a turning point, here's a turning point, here's a turning point, here's a turning point. That's 4 turning points, right? Plus 1 means our possible degree is 5. So we think that we might have 5 roots here. 5 roots, right? So we're going to count the amount of real roots we can find, and then that'll help us predict the imaginary. Okay, so we go back, we look for our x-intercepts. Well, there's an x-intercept there, and there's one there. This crosses, so that's 1 real. It's a single, right? This bounces, so that's a double, so that's 2 real. All right, so that's 2 real, 1 more real, that's 3 real. So the number and type of roots, well, we must have 3 real roots. And if we know we're supposed to have 5, well, that leaves 2 imaginary. And that's a good number for imaginary. Like if for some reason we got 1 imaginary or 3 imaginary, we would know we made a mistake because those always come in pairs. It should be 2 or 4, right? So that's just what we want to do to get us started with these so we know what to expect. We can predict our values. Okay? Moving on to the back. All right, finding imaginary roots. So there's a few steps we want to follow here. All right? So our first step is we're going to just do what we usually do, right? Use our factoring methods first. See how far we can get. Right? It's not going to get us all the way when we have imaginary roots, but it'll get us some part of the way, right? And then when we can't factor anymore, we set up the zero product property. Set everything equal to 0 that is a factor, right? Even if we're not fully factored, even like if in our example we have a binomial and then a quadratic, we set them both equal to 0 because we've gone as far as we can with factoring. After that, we use either isolating the square, which is our square rooting both sides thing, or quadratic formula, to solve the piece that was not factorable, that wasn't a binomial, that isn't just super easy to zero product property, right? And then the last thing we do, and it's kind of optional, but I highly recommend it, sketch it to sense check to make sure it looks like what we would expect based on our results. Okay, so we're going to do a couple of examples, and then we'll be done. All right, so we start out with this one, right? We're going to set it equal to 0 because we're trying to solve, right? We're trying to find those roots just like we have been doing, right? Now, if I set this equal to 0, I notice I have x to the 4th, x squared, and a number. So I'm going to try for quadratic form. So I'm going to magic x, and I have -8 and 2. So I need two numbers that multiply to give me -8, add to give me 2. That turns out to be 4 and -2. So I start to factor this. 0 equals x squared plus 4 and x squared minus 2. Okay? I've factored this as far as I can. That's non-different to perfect squares. I can't keep going. Either is that, so I zero product property. So I say, okay, x squared plus 4 equals 0. X squared minus 2 equals 0. And I have to solve each of these using isolating the square. So let's see what happens. Well, here, I would minus 4 on both sides. I'd get x squared equals minus 4. Then I'd square root both sides. And I get x equals plus or minus the square root of -4. Well, we just talked about that. Square root of 4 is 2. And then we know the negative gives us an I. So this is x equals plus or minus 2i. And that is my two imaginary roots in this scenario, which is a good number because that's a pair. We're supposed to have even amounts. Here, I would do a very similar thing, add 2, add 2. I'd get x squared equals 2, square root, and I'd get x equals plus or minus the square root of 2. And those are my two real roots. Okay, so I got two real roots, two imaginary roots. That's 4 total roots. That makes sense because our degree was 4. Now, I said we want to sketch this to make sure it makes sense, right? So if I'm sketching this, well, first of all, I know I have a y-intercept of -8. So I would kind of estimate a -8 down here. I know I have two real roots at positive square root 2 and negative square root 2. It's like 1 point something, so don't need to be crazy with that. I'll just put a root here and a root here. Now, I also know that because this is a positive quadratic function, they usually look like this, right? So what must happen is you must come down through the real root, go through the intercept, y-intercept, and then come back up, right? So it might look something like this. Right? And there you go. You have a quadratic function. It's got 3 turning points. It's got 2 real roots, but it must have 2 imaginary roots because it's only got 2 x-intercepts. They're both single roots. They just cross, right? So you know that it feels right to you. Okay, one more. Here you have a sum of cubes situation, right? So I'd set it equal to 0, and then I would factor it, right? It would be x plus 3, because that's my a and b, and then I would have x squared minus 3x plus 9. Now, we talked about during our sum of cubes lesson that this part is not further factorable. It never will be. It just doesn't work. So that means I'm fully factored. I have to set them both equal to 0 and 0 product property. It's already equal to 0. So I say, okay, x plus 3 equals 0. And x squared minus 3x plus 9 equals 0. This one will be easy, just minus 3, x equals -3. That is one real root. And then in this case, I'm going to have to use the quadratic formula to find my x. So I'll do that. Say x equals -b, so that's 3, plus or minus the square root of b squared, so that's -3 squared, minus 4 times 1 times 9, all over 2 times 1. Clean that up a little bit. We get 3 plus or minus the square root of whatever that is over 2. Now, that whatever that is turns out is minus 27, right? Just use your calculator to help you with that. Now minus 27, got to remember what we do when we have the square root of a radical that we can break down. This is going to break down into square root of negative 1 times the square root of 9 times the square root of 3. Square root of 9 we can do, that's plus or minus 3. Square root of negative 1 is I. So I end up with plus or minus 3i square root of 3. So this piece right here goes in where there was a square root of negative 27. And I get x equals, let's switch back to red, x equals plus or minus, 3 plus or minus 3i square root of 3 over 2. Okay? So there are your two imaginary roots, and that's a good amount because it's even. Okay? And two imaginary, one real, that's 3 total. We started out with a cubic function, so that makes sense too. And then if you wanted to, you could sketch this. Now we know it's a cubic function that's positive, so it's going to look like that kind of thing, right? We know it only has one real root at negative 3, right here. And we also know it has a y-intercept of 27, which I know will be much higher than this, but we're just sketching. So we'll say that's up here. So it must start from the bottom, come up here, and go up through there, right? So it's a cubic function. Maybe you can do better than that. I kind of ran out of room, right? It goes through the one real root. It crosses its single root, right? It must have two imaginary roots because it's cubic. So it has 3, and then it never comes back and never touches the x-axis, okay? All right, so that is your skill for the day. You're either using the quadratic formula or isolating the square. You end up with imaginary roots, and then you just want to sense check that it makes sense. Did I end up with a pair of them or an even amount? Did I was I able to make a sketch with that information that actually looks like it could be true based on what I had? Okay, so there you go. Good luck.